So we're in progress. Does anyone have any questions? Speak now or forever ask questions if you have them in the future. Is that clear? You can ask questions whenever. Yes? Is this going to be one of those times where you're not going to respond at all? I feel like I'm
sorry, I couldn't hear.
Oh, can you hear me now?
Yes, it was my mic. It was disconnected. Sorry.
I feel like a commercial. Can you hear me now? So let me do a share. Oh, there's a chat. Who's chatting? All right. Greg, I don't usually keep the chat window open because there's too much stuff on my computer. So instead I use the participant list because you can use yes, no, and all that stuff. So since we don't have any questions, let's jump right into it. I'm going to go kind of fast because we have a lot of material that I'd like to cover. And all of it is important. So let me get some blank pages here. Where is my blank paper? Huh. Well, it looks like I have to jump up and grab some blank paper. But in the meantime, I'm going to change my share to my desktop. So what we're going to do is we're going to be talking about compounds. And the first thing I'm going to tell you are that there are two types of compounds. One type of compound is called molecular, and the other is called ionic. Now, there are characters of ionic compounds and molecular compounds that you should know. For instance, ionic compounds, they're held together by ionic bonds. I like that. They're usually a metal and a non-metal. And of course, I'm talking about elements. The metal is going to be a cation, and the non-metal is an anion. Cation simply means a positively charged ion. Anion means a negatively charged. The smallest unit is or are the ions. What else can I tell you about them? They tend to be solid at room temp. In fact, I can only think of one ionic compound that's not a solid at room temp. It's more like a slushy thing, but it's mostly solid at room temp. But these guys are solid at room temp. They tend to be not water soluble. If they are water soluble, the solution conducts electricity. They form a three-dimensional crystal lattice of ions. What else can I tell you? They're brittle. I'm sure I can think of a few more things after this, but I'm not going to bother right now. Molecular compounds, they're held together. The atoms are held together by covalent bonds. And it's usually two nonmetals. And the smallest unit is the molecule. And for these molecular compounds, some are a gas at room temp, like butane, methane. Some are a liquid at room temp, like gasoline. And some are solid at room temp, like sugar. Some are gas, some liquid, and some solid at room temp. Many are not water soluble. If water soluble, they tend to not conduct electricity. Many of them are crystalline, but it's not a three-dimensional crystal lattice. And if a solid, many of them are brittle. Two more things here. These tend to have low melting points and low boiling points. And these guys tend to have high melting points and high boiling points. For instance, if we talk about a molecular compound that melts, sugar melts in your pots and pans, on the stovetop. On the other hand, if you put salt, which is sodium chloride, sodium a metal and chloride a non-metal, salt will not melt in a pan on your stovetop because it doesn't get hot enough because the melting point is too high. Okay, any questions about these attributes or properties of molecular compounds versus ionic compounds? Okay, there being none, let's move on. Let's take a look at molecular compounds and how to name them. Now, we're doing molecular compounds first because they're easier than ionic compounds. So we're looking at naming and formulas. And I'm going to check something real quick here. Okay. I'm just checking to make sure that I am recording this. So for molecular compounds, we're going to name binary molecular compounds. And that means two types of elements. That doesn't mean there aren't trinary molecular compounds. We're just going to name binary. Okay, so we have the naming. And I'm going to give you some examples, and then we'll look at the rules. CO2 is called carbon dioxide. CO is called carbon monoxide. N2H4 would be called dinitrogen. Tetrahydride. So if we take a look at just these three examples, you can see that when we name them, you name the first element first and you name the second element second. Furthermore, the first element gets a name that sounds like the element. Carbon, carbon, nitrogen. Furthermore, if there's more than one of the first element, you use a prefix. Let's look at the prefix you need to memorize. So if the prefix is 1, or if the number is 1, the prefix is mono. 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. So you should memorize those prefixes. Most of them you probably have heard of before, like certainly you've heard of an octopus, which has 8 tentacles. Octa is 8. Certainly you've heard of a decade, which has 10 years, so deca. Nona sounds like 9 in a way. Penta, pentagon, tetra, tetrapod, tricycle. It's not called a dicycle, but di is probably something you've heard of before, and mono is something you've heard of before. I'm not sure that you've heard of hexa or hepta. Now, the way I actually remember these last 4 is because of the month of September, October, November, and December. So hept is like sept, oct is like oct. And so I know that September is the 9th month of the year, and October is the 10th, and November the 11th, and December the 12th. But that wasn't the case a little over 2,000 years ago. September used to be the 7th month of the year. And that's why September is called September, because it's the 7th month. Was the 7th month. Correct myself. October used to be the 8th month. November used to be the 9th, and December used to be the 10th month, except for also there was winter a little over 2,000 years ago, and it was an indeterminate amount of time. And someone said, this is baloney. We need to have winter be a precise amount of time. Let's invent a couple of months. So they invented January and February. And instead of making our lives easier and making January the 11th month after December and February the 12th month after January, they decided to make January the 1st month and February the 2nd month, which is ridiculous. And the reason they did that is just to mess with chemistry students in the future. So they succeeded. So you might be wondering, is any of that story true? And the answer is absolutely. Oh, you're not wondering, is he? Or you are wondering? Or did you know that story beforehand?
No, I heard it in your
Oh, you watched the previous
lecture.
Okay, well, it's a true story. Okay, so these are the prefixes you need to know. Any questions about that? So you should be able to go back and forth between these, but now I'm going to give you the IDs. Basically, to name these, you use prefix, element, prefix, elemide. Now, for the first element, you can see for carbon, we didn't use a prefix. If there's only one, don't use a prefix. If there's more than one, use a prefix. For the second one, regardless, you use a prefix. And irregardless, you use a prefix, which we know isn't a word. So let me give you all the IDs. Hydrogen is hydride. Carbon is carbide. Nitrogen is nitride. Oxygen is oxide. And fluorine is fluoride. And then you have phosphide, sulfide, chloride, and then you have bromide and iodide. And those are the ones you should know. You don't need to know selenide and telluride. That's all right. So, any questions about the IDs? So remember, molecular compounds, we're looking for 2 types of elements, and they're both going to be non-metals. Let's add that in. Doesn't hurt to have it there again. And when you name them, you name the first element first and the second element second. Also, when you look at the arrangement of the elements, often if there's a hydrogen, it goes last. Often, not always. And for the rest of them, usually what happens is you put the element to the left on the periodic table first. So carbon's to the left of oxygen, it goes first. Here's another one though. This is sulfur dioxide. So if the two elements have one, if they're both in the same group, you put the lower one in the group first. Okay, so let's try some problems. Okay, what I want you to do is take a moment and see if you can name these 4 compounds. When you're done with, and I'm going to make you focus on A and C. Focus on A and C. I'm not messing with you. I'm actually trying to get it to be more clear. Okay, try to focus on A and C. And when you get those answers, give me a little thumbs up.
Tony, in the list that you gave us before this with the hydride, carbide, nitride, you had them listed separately, but I don't know why. Like, did you explain that or?
The only reason I listed them separately is because I wanted to show kind of where they were relative to one another on the periodic table.
Okay, that's what I thought, but I just wanted to make sure. Okay.
And then I gave up writing the symbol of the element when we got to phosphide and so forth and so on.
Okay.
Because I ran out of room on my paper. Okay, how are we doing on A and C? Because those are the 2 we're going to look at. I know one person's done with them. Are we all done? Okay, let's take a look at A, dinitrogen, pentaoxide. A lot of times when we have 2 vowels together like this, we get rid of one of these. And we like to call this pentoxide. C is going to be oxygen difluoride. So you see in one of these, you have an oxide, and the other one, you have an oxygen, simply because in the first one, the oxygen is written second, so it's oxide. And in the first one, or in the second one, I'm not sure if I said that right. In the first one, oxygen is second, so it's oxide. And then in the third one, oxygen is first, so it's oxygen.
Now, when would you use mono? Like, wouldn't that be mono difluoride?
No, you only use a prefix on the first one if there's more than one. Think carbon dioxide.
But mono is one.
I know mono is one, but think carbon dioxide. Do we use monocarbon?
Oh, yeah, okay, that makes sense, yeah.
So we're not going to use mono oxygen here. You don't use mono for the first element. Okay, that's the big difference between, well, that's not the big difference. That's the difference in prefixes between the 2. Don't use mono for the first. Always use a prefix for the second. So that can be a little confusing, but you know, this is the way we've been doing it for decades. Okay, let's move on from that one then. And let's see if you can write the formulas for A, B, and D. When you're done, give me a little thumbs up or something. Okay, are we ready to go on A, B, and D? Because we didn't talk about C and E, so you can't do those. Okay, well, I'm going to go ahead and go with A. Bromine is Br, and there's only one because there's no prefix used. And then trifluoride would be F3. B, the symbol for xenon is Xe, and difluoride is 2. And D, diphosphorus, and tetrafluoride, 4. So how would you name, or how would you write the formula for the following? One of the most dangerous compounds on Earth. What's the formula? This kills hundreds of people every year. Have you got it?
Water.
H2O. Yeah, so they drown in it, right? Or they get pneumonia and that kills them that way. So you could say that it has killed over 400,000 people in the United States this year, or last year, I should say. Because most of the people that die of coronavirus died from their lungs not working anymore. They basically suffocate. Okay. So any questions about those molecular compounds, how to name them, how to get the formula? There being none, then we're going to go on to ionic compounds. So I'm going to teach you some things about ionic compounds that you definitely will want to know to be able to get formulas and names of compounds. So I'm going to zoom out here. So first of all, for ionic compounds, they tend to be a metal and a nonmetal. The metal is the cation, the nonmetal is the anion. The cation is something with a positive charge, the anion is something with a negative charge. And don't let me hear you saying cation, because that's not cation. I don't want you leaving my chemistry class, going somewhere in the world and saying cation, and then they're going to come back to me and say, what were you teaching them, Tony? Cation, okay? Anion. All right. When you write the formula, you write the cation first and the anion second, because that's just the way it's always been done. Let's look at cation formation. So sodium is an atom with 11 protons, and most of them have 12 neutrons. So this is the isotope that has 23. And since it's a neutral atom, it also has 11 electrons. Now I'm going to put a little arrow here and a little arrow here. So we're going from here to here. This is what happens to sodium when it becomes an ion. Now, this sodium atom is very unstable. If you were to touch this with your hand, it would react immediately. This is what happens to the sodium atom. So you can see that the nucleus doesn't change. And that makes sense because the sodium atom becomes a sodium ion, still has the same number of protons. Now you can see I've drawn this as being smaller than this because it is. And it's got only 10 electrons. So what's the symbol we draw for this? And the answer is you draw Na because of the 11 protons. And then when you think about the charge, since we have 11 protons and 12 neutrons, the total charge in the nucleus is plus 11. And you add to that 10 electrons and you get a total charge of plus 1. So how do we write this in the symbol? Like that. Now, whenever we write a reaction, we like to account for all of the matter on the left and the right. Can you see that we have 12 neutrons and 12 neutrons, so neutrons are accounted for. 11 protons and 11 protons, so 11 protons are accounted for. But we have 11 electrons and only 10 electrons, so where's the other electron? Well, to account for it, we say we get this ion plus an electron that's no longer part of the ion. So that would be written like this above. So below we have a drawing of what happens to the atom, and above we have the symbolism that we use to represent the same thing. And this is cation formation. Now I'm going to test your abilities based on what you've just drawn. So give me a thumbs up if you're ready to go on. Are you good, Izzy?
Yeah, I just put my thumbs up. You didn't see it?
Oh no, I'm looking at the participant list. I'm not looking at your image.
Yeah, that's where I put my thumbs up, on the participants list.
Try it again.
That's strange. I just removed it and now I'm putting it on again.
I don't
It's
see
not
it.
coming through. What,
Try
can you see the
yes.
yes?
I see the yes, but I don't see the thumbs up.
I'll just do yes from now on then.
Sounds
I
great.
guess it's not going through.
So now what I'm going to draw for you is something else. Magnesium can become an ion. And what it does is it becomes a +2 ion. And that means that 2 electrons come off of it. Magnesium is number 12, and most of your magnesiums have 12 neutrons. And a neutral magnesium atom has 12 electrons. So over here, we're going to draw this arrow. We're going to do a +2 electrons. What do you draw here? Give it a try. And when you have an idea, give me a thumbs up or a yes. Okay. So what are we going to draw in the middle?
The nucleus.
12 protons and 12 neutrons.
And then
And
with
what are we going to write around the outside?
the outer 10 electrons.
Why is it 10 electrons and not 14?
Because it's been you reduced it by 2.
Right.
You removed 2 electrons
Another way to answer it is if you had 14 electrons, this would be a -2. So this
Right.
is correct. Tell me why this is wrong. Let's see. So here we have 12 electrons and we still have 12 electrons. We still have 12 neutrons, but we have 14 protons. And since there's 14 protons, this will have a charge of +2. Why is this wrong?
You can't add
Different-
protons.
Different
go ahead.
element?
Go ahead, Greg.
Wouldn't that be a different element?
Absolutely, and that's why it's wrong. This would be silicon with a 2+ charge. So my point is that when you become an ion, you cannot gain protons or lose them. That means you change to a different element. That doesn't happen in chemistry. You have to gain electrons or lose them. And this is considered to be losing electrons, even though it's a plus sign. Okay, so what can happen with oxygen is that oxygen can become a anion. So now we're looking at anion formation. So with an oxygen, if I draw it out, most oxygens have 8 protons and 8 neutrons and 8 electrons. Over here, because there's a -2 charge, we have to add 2 electrons. So 8 protons, 8 neutrons, and we draw it larger, it's got 10 electrons. And here you can see that we have to add 2 electrons to this side to make it work. So overall, we have 10 electrons, 10 electrons, 8 protons, 8 protons, 8 neutrons, 8 neutrons. So we can see that to form an anion, you have to get electrons. And to form a cation, you actually lose them. This is considered losing. So when you lose electrons, that electron becomes a product. And when you gain an electron, that electron is a reactant. So why do these atoms form these ions? These are real ions that form. These aren't like pretend ones. These are real ions that form. And the question is why do they form these ions? And the answer is because they become stable. And once you become stable, it's hard to change them. Now, if we take a look at these 2 examples here of oxygen and sodium, notice that when they become stable ions, they both end up with 10 electrons. What neutral atom has 10 electrons? So we look at our periodic table and we look for the atom that has 10 protons, and that's neon. Neon has 10 protons and 10 electrons. And what do we know about the noble gases? They're inert, which means they're unreactive, and they're rare. The inert part is what we're interested in. Inert means they're unreactive. Unreactive means they're stable. So it turns out that when atoms tend to end up with the same number of electrons as a noble gas, they tend to become stable. Now, oxygen ion, the oxide ion, is not as stable as a noble gas because of the following. A noble gas atom has no charge, therefore it is not attracted to other atoms. The oxide ion has a negative charge, therefore it is attracted to positive ions. So these 2 ions would be attracted to one another. Even though they're stable like noble gases, they're still attracted to the opposite charge. Okay, so that's the first thing about ionic compounds, how ions are formed. Secondly, there are different types of monatomic anions. So we're going to look at, actually, let's look at cations first. Cations. So there are monatomic cations. That means a cation with one element, or one type of element, I should say. So some of them are fixed charge, and that means that regardless of the ionic compound they're in, they have the same charge. So you need to memorize all of the fixed charge ions and how to name them. So let's go over the fixed charged ones. Are you ready? Yeah. Okay, now I want you to recall that we said that metals form the cations. So we're really talking about metals in 1A, metals in 2A, and metals in 3A. These guys all form a +1 charge. These guys form a +2 charge. These guys form a +3 charge. So for instance, aluminum is +3. Lithium is +1. Magnesium is +2. So that's the charge you expect for anything in 1A, +1, anything in 2A, +2, and metals in 3A, +3. In addition, there's zinc, which is going to be a +2, and there's silver, which is going to be a +1. Those are all of the fixed charge cations. How do you name the fixed charge cations? Well, it's pretty simple. Lithium with a +1 is called lithium ion. Magnesium with a +2 is called magnesium ion. Zinc with a +2 is called zinc ion. And so you might ask yourself, why don't we tell people the charge in the name? And the answer is, we assume you have a periodic table. So when we say lithium ion, we think you're going to go to your periodic table, see it's in group 1 and say, oh, it's a +1. I know the charge. So the assumption is that you can figure it out because you've been taught how to figure it out. So these are all the fixed charge ions. 1A, 2A, the metals in 3A, silver and zinc. Oops, sorry about that. Any questions about the fixed charge ions? So what I'm going to do here is I'm going to put these in green. So those are in green. Now, what about the ones that are not fixed charge? The ones that are what we call variable charge. Actually, I don't want that to be green. I want that to be purple. Where are the cations that are variable charge? And the answer is everywhere else. All of the other metals. Now remember, these are the metalloids, and the non-metals are to the right and the metals are to the left. So these guys are variable charge. For instance, there is an atom in here called tin, an element called tin. There is a tin with a +4 charge, and there's a tin with a +2 charge. Clearly, they have different charges, and clearly, we need to distinguish between the two in the name. So the way we do this is we call this guy tin 4, and we call this one tin 2. So these are Roman numerals to describe the charge on the ion. So all of these purple ones, you have to tell people the charge in the name. So let's talk about Roman numerals. You need to know the following 6 Roman numerals for the following amounts: 1, 2, 3, 4, 5, 6. And I'm going to put RN for a Roman numeral, not registered nurse. For Roman numeral 1, you use a I, and you can use an I like this, or you can use an I with crossbars. I don't care. I tend to use this guy and not the one with crossbars. 2 is 3 I's. 3 is 3 I's. So either one. I'm going to skip 4. 5 is a V. Now, when we look at 5, which number is the 1 before 5? The 1 before 5 is 4. So here's a 5. The 1 before 5 is 4. So when you look at 6, which number is that compared to 5? It's the 1 after 5. So here's the 5, and we put the 1 after 5, and you have 6. A student taught that to me years ago. They said that's how they remember 4 and 5. 4 is the 1 before 5, and 6 is the 1 after 5. And I thought it was a very good way to remember that. So any questions about the Roman numerals you need to memorize? Now, this is the standard way of naming these nowadays. Before, we used to have another way of naming them. And I'm going to show you the names, so some of the names, not all of them, so that you understand why we don't do that anymore. So there used to be an Fe2 plus. What do we call that now? If you get it, give me a little yes or something. What do we call that? And the answer is iron 2 ion. It used to be called ferrous. And then there's an Fe3 plus, which was called ferric. And of course, when you have names like this, you have things like this. Where this is a Ferris wheel. Okay. So there's copper 1 and copper 2. This one is cuprous, and this one is cupric. So when you take a look at this, you go, oh, I thought maybe the S's would be 2s, but they're not. And then you look at this and you go, oh, well, if you know the us, you can figure out the ick because they differ by 1. And that's not the case. There's tan us, and then there's tan ick. And so you might think, okay, ick is +3. And it's not, it's +4. Can you imagine how tough it is to learn how to name all of these guys the old-fashioned way? So instead, we now have iron 2 ion, iron 3 ion, copper 1 ion, copper 2 ion, tin. Are you guys with me that this way is a lot better and easier to understand? Okay? And that's the way we're going to do it in our class. You might have some problems where you look in the book and it says, what are these? Don't worry about it. It's not going to be on a test or a quiz. Okay, so now we've learned how to name monatomic cations. So we've got cations, monatomic. We've got the fixed. We've got the variable. And now we have polyatomic. So it turns out that polyatomic ions, the atoms are bonded together like in a molecule, except the thing has a charge. There's only one polyatomic I want you to memorize, and that's NH4 plus. It's called the ammonium ion. Now, this doesn't mean it's the only polyatomic cation, but it's the one that you should memorize. Any questions about these cations? So if I draw my periodic table again, fixed, fixed, fixed. The rest are variable. Okay, so F is fixed, V is variable. Okay, this is to kind of give you a visual of what's going on. What are these guys going to be? They're going to be anions. Okay, now let's take a look at the anions. You need to memorize the following anions. We've got monatomic. So the monatomic anions that you need to memorize, I'm going to give you this first one. This is H minus. This is hydride. And we've seen that word hydride before in molecular compounds. So how are you going to know whether you have a hydride ion or a hydride from a molecular compound? Well, it really depends. If you have NaH, metal, non-metal, that's ionic. If you have let's see, if you have N2H2 or H4, excuse me, these are all non-metals, so this is molecular. So this is a molecular hydride. That's how you tell the difference. Metal, non-metal, non-metals. Okay, then there is carbon, which forms a -4 charge. It's called carbide ion. And then there's nitrogen with a 3-, which is nitride ion. There's oxygen with a 2-, which is oxide ion. And there's F with a negative, which is fluoride ion. There is no non-metal below carbon, so there's no ion we need to worry about here. There is a non-metal below nitrogen. It's phosphorus. It forms a -3 charge, and it's called phosphide ion. And then there is a non-metal below oxygen, that's sulfur. It forms a -2 charge, which is sulfide ion. And then we have chloride ion. So you can see that in the groups, they form the same charge on their anion. And if you look at the period 2, where you have neon, fluorine, oxygen, nitrogen, carbon, beryllium, and then there's nothing right there. What are the charges that these form as anions? Well, you start with neon, 0, -1, -2, -3, -4, and that's the way it works all the way down the list for the nonmetals. Okay, so that means bromine is going to be our negative, which is bromide. And I will be I negative, which is iodide. So you want to memorize all of these. Now we're going to move to polyatomic anions. And this is where things really get interesting. There are hundreds of polyatomic ions. So what do we want you to memorize? We want you to memorize the most common ones. So here they are: OH negative, hydroxide. How are we going to know when we look at this name that this is simply not a hydrogen ion? Well, it's got two parts to the name, the hydrogen part and the oxygen part, hydroxide. There's this guy, which is called nitrate ion. There's this guy, C2H3O2 -1, which is called acetate ion. There's ClO3 -1, which is called chlorate. So these are all of the ones that are a -1 charge. There's sulfate ion. There's carbonate ion. So these are the ones with a -2 charge, and you should memorize this one also, which is the phosphate ion. So these are all common polyatomic anions. Once you have these copied down, give me a little thumbs up or something. And while you're doing that, I'll be right back. Okay, remember, give me a little thumbs up or yes when you're done. Excellent. So now there are variations of these guys here. So I'm going to give you the H plus variation first. And the H plus variation for phosphate looks as follows. So we have phosphate ion. What happens if I add an H plus to this guy? Well, we get HPO4. What happens to the charge? When you have a +1 and a -3, they add together to be -2. So it's got a different formula than the phosphate ion, different charge. What do we call it? Well, we call it hydrogen phosphate. So you should know that one. What happens when we add an H plus to hydrogen phosphate ion? So if we add an H plus to this, H plus and this, we now get 2 hydrogens. What happens to the charge between +1 and -2? It becomes -1. What do we call it? We call it dihydrogen phosphate. Now, even though this is made up of, by combining 2 ions, this itself is only 1 ion. So it's kind of like this is a piece of clay, this is a piece of clay, and when you put them together, you get one bigger piece of clay. Okay, so that's the hydrogen variation. If we add one more H plus, we get H3PO4. It no longer is charged, and so it's not called an ion. In fact, this is called phosphoric acid. Okay, so that's the H variation. And Each of these has that variation. For instance, nitrate ion, if we add an H plus to it, we get HNO3, and that's neutral. So it's not an ion anymore. What do you call it? You call it nitric acid. So eventually nitrate forms nitric acid, sulfate forms sulfuric acid, carbonate forms carbonic acid, and phosphate forms phosphoric acid eventually. The other variation I want to show you is what I call the per 8-ite hypo variation. So I'm going to write ClO4, ClO3, ClO2, and ClO as a list here. The one ion we should know is the chlorate, and that's a -1. What is the charge on this guy with an additional oxygen? It turns out it's -1. How about this guy with one less oxygen? It's a -1. How about this one with even one less oxygen? -1. So this is the only one that we've talked about before, chlorate. So what is the per 8-ite hypo variation? One less oxygen, same charge, chlorite. So this nitrate has a nitrite, one less oxygen. This sulfate has a sulfite, one less oxygen. Not all of them have this variation. Now, what happens when you have one less oxygen than chlorite? You have hypochlorite. You may have heard the term hypoglycemia, low blood sugar. Hypochlorite is low oxygen. So what do we call this one? We call it perchlorate. One more oxygen, and we use per instead of hyper so that it's easier to distinguish between these two. If you say hyperchlorate slowly, and if you say hypochlorite slowly, you can distinguish them. But if you were to say hyperchlorate and hypochlorite, it'd be hard to distinguish the two. So drop the high off of this, and perchlorate is clearly distinguishable from hypo. So any questions about these variations? Are we good to go then? So in just the next few minutes here, I don't want to take too much longer. I want to show you for ionic compounds, naming and formulas. So I want to teach you how to take the name of an ionic compound, figure out what the ions are, and then figure out the formula. But I also want to be able to give you the formula, have you figure out the ions, and have you figure out the name. I want you to be able to travel both ways on this street. And I'd like you to be able to start at either end or in the middle and get to either end. So let's take a look at some formulas and see if we can get the name. Okay, so these are ionic compounds. So the first formula I'm going to give you is FeO, and let's figure out the name. Now, one of the things I may not have told you before is that when you write the formula, you need to know the following for the formula. It's neutral. So when you add up the charges and all the ions, it's neutral. And it's also going to be the simplest ratio. So if you can have 5 of one and 5 of another, and it adds up to be neutral, you don't say that the formula is 5-5, you say it's 1-1. So the simplest ratio and neutral. So with that in mind, I'm going to write these out kind of in steps. The first thing you do is you say, oh, I've got an iron ion, and I've got a oxygen ion, and the cation always goes first. So that's a cation and that's an anion. Your next step is to say oxygen is -2 because it's a anion that is always a -2. And then your next step is to say that, well, for this to be neutral, the iron has to be +2, and then it's neutral. We don't get to adjust how many of each. It's 1-to-1, it says right there. So now that we know what the ions are, this one's called iron 2 ion. This one's called oxide ion. And now we're ready to write the name. And when you write the name, you write iron 2 oxide. You don't write ion here. It's iron 2 oxide. So any questions about how we came to that name? Or are we good? I think I'll just ask you, are we good? Okay,
I think I'm good at, sorry, I'm just writing it down
that's all right. That's why I'm asking you, are you good?
now, yes.
I'm not asking you because I'm Santa Claus and I want to know whether or not you deserve a present. Although I am starting to look kind of old and Santa Claus-ish. Okay,
Are you
So-
saying there's presents involved?
you're going to get a big present on exam day.
I like mine. I like
You're gonna get a
A's.
surprise on exam
You,
day.
you want to give presents. I like A's. I think Izzy likes the same.
Yeah.
You know, I would love to give presents, but I'm not allowed to. And the way Santa Claus would say it is, you know, you don't get presents, you earn them. Okay, so what are we going to do here? Fe, Fe, O, O, O. Which ones of these should we know the charge on automatically? The oxygens. So those are the oxygens. And can you see that the total charge is -6? What does the total charge on the 2 irons have to be to make it neutral?
6.
+6. So what do the charges have to be on those iron ions to make a +6 charge overall? And trust me on this one, you're not going to say, well, one of them could be a 1 and one could be a 5. You give them both the same charge.
So what, 3 and 3? Yeah.
Right. Okay. And so what do we call this? We call it iron 3 ion. And these are oxide ions. And when you put the name together, it's iron 3 oxide. And you'll notice here, even though we have 2 of these, we don't use a prefix. Even though we have 3, we don't use a prefix. So that's how you take the name and get the formula. The trick is when you're given the formula and you break it down into ions, there better be at least one ion where you know the charge. If there isn't, good luck. Okay, now, why don't we need prefixes here? Well, let's take iron 3 oxide, and now we're going to do the reverse. We're going to take the name, we're going to get the ions, and we're going to get the formula. So we have the name, iron 3 oxide. Let's figure out the ions. Iron 3 is by far the easiest of these two. It's iron with the +3. Oxide, because of where it's in the periodic table, it's O2 minus. And to figure out the formula, we're going to do something called switch and simplify. So here's what the switch means. This 2 becomes the number of irons that we have. This 3 becomes the number of oxygens that we have. To simplify, you ask yourself, is the ratio of 2 to 3 as simple as it can be, or can I divide something into each of these and get whole numbers and make it simpler? And the answer is this can't be simplified. So this is iron 3 oxide, and I'm going to flip the page over. And remember, for iron 3 oxide, we had that formula here. We got to that name. Now we just took the name and we got to the same formula. So the switch and simplify works great. I'm going to give you an example now where you're going to work it out. You're going to get the charges on the ions. You're going to do the switch and simplify, and you're going to get the formula. Okay? Tin, 4, sulfide. When you're done, give me a thumbs up.
Symbol for tin.
SN. Yeah, it's one of those weird ones like sodium, where sodium is not an S, it's Na.
Didn't realize my thing was on.
Oh, well, I'm sorry for, that's all right. No big deal. Zero, -1, -2. Okay, here's the switch. The 2 becomes the subscript for tin. The 4 becomes the subscript for sulfur. Can this be simplified into an equal ratio? 2 to 4 could also be thought of as 1 to 2. This is simplified. This is tin 4 sulfide. Any questions there? Okay, how about this one? Chromium 4 sulfate. Not sulfide, sulfate. Chromium is Cr. So of course, chromium is a College of the Redwoods favorite element. So give me a thumbs up when you're done. Okay, so I have a 4+, and if I ask you to get the name of something or get the formula of something, show your work, this is the kind of stuff I'm asking you to do. So this is what you get. Now sulfate, we need 4 of them. This is wrong because this actually says you have 44 oxygens. And if we meant 4 sulfates, that's how you do it. Now to simplify, we look at this 2 and this 4 on the outside. And that's the simplified version for chromium 4 sulfate. Any questions about this one? Okay, no questions then. This is homework. Name each of these, and you're going to find that the name is really interesting compared to the formula. Okay, so thanks for listening. Hopefully I will see you tomorrow during the day because there's no night session.
What is the second one? Just CUS? Or-
Yeah.
Okay.
So they're both copper sulfides, but the question is, what is the name of each one? And I'll give you a hint. One's copper 2 sulfide, one's copper 1 sulfide. So naturally that's copper 2 sulfide, right?
Mm-hmm.
No.
Mm-mm.
Find out. Go through our process, get the name, and you'll find it interesting. Because in parentheses, that's not how many, it's the charge.
Mm-hmm.
Okay. All right. Thanks for attending, people. I hope to see you tomorrow during the day. Toodles.
Okay. Bye. Good night.
And you'll post the your day lecture on the night, right?
I'm going to be honest with you, Greg. If I record it, I'll post it. If
Okay.
I don't record it, I won't post it because I've been making the mistake of not recording sessions lately. I don't
Not
know
a problem.
why.
Well,
But-
again, hey, I appreciate what you got right now. Thanks anyways.
Yeah, so I will definitely try. And that's why tonight earlier you heard me say, am I recording? Because I'm freaking out because I forgot to record the afternoon session.
Gotcha.
So
Okay.
luckily for today, we've got the morning, we've got the night, and that's 2 out of 3. That's not too bad.
I know it's a good thing you do it 3 times.
Yeah, well,
Okay.
I do it 3 times because, some people can show up in the morning, some can show up in the afternoon, and some can show up in the early evening. I'm not going to do one in the middle of the night, like at midnight.
Thank you.
Well, I appreciate you doing it at night. It makes it
Yeah.
easier for me.
I do that for people who work during the day. All right.
All
Good
right.
day.
Thank you. Have a good night.
Good night.
Thank you. Good night.
Good night.